Hello. We're going to look today at Newton's second law, following straight on from the previous examination of Newton's first law and momentum. And we'll start with this little picky of the big man himself, not the nicest guy on the planet, but certainly one of the most influential over the last few hundred years in the fields of science and engineering. And his second law says, in a more modern language, the rate of change of momentum is directly proportional to the unbalanced force and is in the same direction. So that's a building on from the Newton's first law we looked at. So Newton's first law really describes, it is a simple statement that if you have an unbalanced force, you have acceleration. If you have balanced forces, you don't have acceleration. Newton's second law gives you what you need to know, because it says, okay, under what circumstances and given certain conditions, what will be the magnitude of that force and what will be the direction of that force. And the magnitude of the force is determined by, determines the rate of change of momentum. So last video we introduced the concept of momentum, and now we see why, because Newton's second law is best described as a change of momentum. So, and how quickly something changes momentum. So the momentum you remember is mass and velocity, and it's a combination of those two things. And so if you have a large force, a large unbalanced force, that momentum can change quickly. If you have a small unbalanced force, it will change slowly. And the direction of the acceleration will always be in the same direction as the unbalanced force. Looking at that in kind of a bit more symbology terms, we have our little ball here, which is on the left hand side at some point in time. We'll call that time t equals 0. And on the right hand side, sometime later, t equals t. And it experiences a force. It's traveling at an unbalanced force. It might experience many forces, but that F is the unbalanced overall force. It has an initial velocity u, and it accelerates with acceleration a until it reaches a final velocity v. Change in momentum. Now remember that all of these are vector acceleration and the different velocities and the force, and the momentum itself is a vector quantity. So the change in momentum is the delta p is the final momentum minus the initial momentum, mv minus mu. And on the green arrow there at the bottom right, you can see mv and minus mu. So we flip that arrow around and we get that change in momentum. We can see how that works as a vector in this fairly simple just forwards and backwards situation. Putting it into more traditional symbols, F equals delta p over delta t, where p equals mass times velocity. So the change in momentum equals the final momentum, mv, minus the initial momentum, mu, divided by delta t. Now we can do something interesting with this equation to give you a different version of Newton's second law, which might be more useful in many situations. If we have mv minus mu, the change in momentum divided by delta t, then given one assumption, we can pull out m and have v minus u divided by delta t. Now, what was the assumption? The assumption, and this is important, the assumption we're now making for this to really work is that mass stays constant. And in the case of a ball here, that's pretty obviously true. And in fact, under many situations, although not all situations, under many situations, we can assume the mass to be constant. So if we can pull the mass out of the brackets, we're just left with v minus u divided by delta t, which is the change in velocity divided by time, and change in velocity divided by time is acceleration. So the rate of change of momentum, if we assume that the mass is constant, is just the same as saying ma, mass times acceleration. So we have F equals ma. F equals ma is possibly the more commonly encountered, in fact, it's pretty much definitely the more commonly encountered form of Newton's second law, but it is also more limited because it does just assume that the mass is constant, and that's not true under all situations. Okay, for example, here those jets of water are exerting a force on this aeroplane when they hit it, but we can't really use F equals ma to calculate because, yeah, they're accelerating, but, what mass are we going to use? It gets a bit more complicated. So rate of change in momentum is the better alternative under that situation. By the way, one final thing. With Newton's second law, should you ever be asked to quote it, merely says that the force is proportional to the rate of change in momentum, or force is proportional to mass times acceleration. We change proportional to an equation by adding a constant of proportionality, k. But we can choose to fix k by setting the unit equal to 1. So k equals 1 means we're kind of defining a unit for force. So if we say the mass to be the SI unit of kilograms, and the SI fundamental unit, and acceleration is the SI derived unit of meters per second squared, then we get, by combining them, the further SI derived units of the Newton. So the Newton, which should have a little n, not a big N, when it's being used as a unit, is the unit of force, and a force of 1 Newton acting on 1 kilogram mass will make that mass accelerate at 1 meters per second squared. An example we can have a look at here is the example of a lift. Here is a lift. Well, behind those doors is a lift. And if that lift is accelerating upwards, now notice the acceleration is upwards. That doesn't necessarily mean that the lift is moving upwards, because it could be actually going down, but it's slowing down to a stop, in which case the force and the acceleration will be acting upwards, or it could be starting to move up and it's getting faster moving up. So the thing to remember there is that acceleration and direction of acceleration does not always match the direction of travel. A lift of 400 kilograms is accelerating upwards at 2 meters per second squared. What is the tension in the cable? Well, if it's accelerating upwards, then there must be an unbalanced force upwards, so the tension must be bigger than the weight. That's kind of a key thing here. So the unmatched force will be F equals T minus mg. So the overall force must be the tension force minus the weight, which must also be equal to mass times acceleration by Newton's second law. So we can, substitute in T minus mg equals ma. So T, the tension force, what we're asking for, equals ma plus mg. The question did say 400 kilograms, and it's at 2 meters per second squared. So we can substitute those numbers in. We can assume that g equals 10, the local gravitational constant, and we get an answer in the tension force of 4,800 newtons. So that's a simple application of a Newton's second law equation. A second example, if you need one, same situation, but it's now accelerating downwards at 2 meters per second. Take a moment, pause the video, think back to the previous question. How does it change under this situation? Okay, so now the weight is going to be bigger than the tension force, because the overall force must be downwards. So the equation changes to F, the unbalanced force, will equal the weight minus the tension. So F equals ma again. So again, we can combine these, very similar to before, just that slight twist. So now T equals mg minus ma. And again, we had 400, so we can substitute those numbers in, and we get a tension of 3,200 newtons. Okay, so that's kind of obvious. The tension is never going to be to zero unless the lift is in free fall. But now we can calculate the actual force on the cable that we need to account for. Okay. Oh, I forgot. There's another example. Two masses are joined by a light inextensible rope. One mass sits on the table and hangs off the edge. Calculate the acceleration of the hanging block. Well, here is an interesting one, because the weight that's being hung is being pulled down. It has, it's moving down and it's being pulling down. It's accelerating down. The mass on the table, that's also got a weight pushing down because it's got weight, but that weight is being cancelled by the normal force from the table. Okay, so the normal force on the table is cancelling out the weight of the silver block, whereas the bronze block, its weight is not being cancelled out. there is tension in the string, and that tension transmits the force between the two blocks, connecting them. So see if you can work that one out. I'm going to pause for a few seconds. Pause the video if you need to. Okay, so let's put this in a nice little diagram. Let's add all the forces so you can see moving from left to right, the weight of the silver block is being cancelled by the normal force. There's the two tension forces, and on the right hand side you have the weight of the bronze block, and that weight must be bigger than the tension force because otherwise it would not be accelerating at all. On the right hand side for big M, we can see that T equals ma. So that's the tension must equal the mass times the acceleration. So the overall force is the tension, and the mass of the block is big M, and the acceleration is a. The acceleration is the same for both blocks because the cable does not get stretched. It's the same length. So both blocks must move together. For the smaller block, the overall force excuse me, is mg minus the tension, again equals ma, this m being the little m because it's the little block. And you can substitute and you can combine and you get a value for the acceleration, which is mg divided by big M plus m, little m. And I think this is kind of intuitively quite clear because mg is the weight of the little block, and there's all the pulling force that's not being cancelled by the normal force is coming from the little block. So it's just the mg, whereas the mass that force is trying to move is actually the combined mass of both the blocks because they're connected by this cable. So I think that's quite clear. Okay, that really is the end. Thank you for your patience, and hope that was helpful.